Hello everyone, myself Dr. B.S. Londe, working as Assistant Professor in Chemistry, Karmavir Bhaurao Patil Mahavidyalay, Pandharpur. In this video, we will deal with the IR Spectroscopy Part 3. In the previous parts of IR Spectroscopy, we have covered Introduction, Principle of IR Spectroscopy, Double beam IR spectrophotometer, Fundamental modes of vibration, types of vibrations, and Hooke's law. Today, we will see the information about factors affecting values of vibrational frequencies, conditions for absorption of radiation and selection rule, fundamental group regions of IR spectrum, in which functional group region and fingerprint region, characteristic absorption of various functional groups, the applications of IR spectroscopy. So first of all, let us see what are the factors that affect the values of vibrational frequencies. When we consider the saturated acyclic ketone, the observed wave number in IR for carbonyl is 1705 and 1725. Near about this value, the carbonyl of saturated acyclic ketone is observed. But when we consider the unsaturated acyclic ketone, the values becomes 1665 and 1685 centimeter inverse. That means the same carbonyl group, when it is present in saturated acyclic ketones and when it is present in unsaturated acyclic ketones, it gives signals at different values. That means something is affecting the value of this stretching frequency, carbonyl stretching frequency. So this is mainly due to the environment of that chromophore. And if we see this example, the environment of this carbonyl. So following are the some of the factors responsible for changing the values of vibrational frequencies, and among those, the first one is physical state, then coupled vibration and Fermi resonance, hydrogen bonding, that hydrogen bonding may be intramolecular or intermolecular, electronegativity, electronic effects, in which we will see inductive effect, mesomeric effect, and field effect. And one more factor which is responsible for changing the value of vibrational frequency, that is bond angles, strain due to bond angle or ring strain. So let us see one by one. The very first factor, that is physical state. The physical state of that compound. When the compound is present in crystalline state or it is in solid state, it has strong interactions such as hydrogen bonding between polar groups of adjoining molecules which are packed in orderly arrangement. And when compound is in liquid or melted solid state, the same intermolecular forces exist. There may be difference between the magnitude of those forces. So, the spectra of the compound which is in gaseous or vapor phase should be considered as ideal because there are no intermolecular forces which are responsible for affecting or changing the ideal values of vibrational frequencies. So physical state affect the values of vibrational frequency. Then coupled vibrations and Fermi resonance. When we consider the isolated CH bond, it exhibits only one stretching frequency, but in case of CH2, that is methylene group, two absorptions are occur which are corresponding to symmetric and asymmetric vibrations. Asymmetric vibrations always occur at higher wave number, than the symmetric vibrations. These vibrations are called as coupled vibrations. These vibrations are known as coupled vibrations, and the reason for calling them as coupled vibration is these vibrations occur at different frequencies than that required for an isolated CH stretching. Similarly, coupled vibrations of methyl group occur at different frequencies as compared to CH2 group. In this case, these will be symmetric stretchings and these will be asymmetric stretchings. Vibrational coupling occurs between two bonds vibrating individually near the same frequencies, and provided that the bonds are reasonably close in the molecule. Strong vibrational coupling between stretching vibrations require a common atom between the groups. The coupling interactions may be both fundamental or the fundamental vibrations may couple with the overtones of some other vibrations. This type of coupling is known as Fermi resonance, and this is known after the name of Enrico Fermi, who first described it. When we take the example of anhydrides show two carbonyl stretching absorptions between 1850 to 1800 centimeter inverse and 1790 to 1740 centimeter inverse with a separation of about 60 centimeter inverse, and these are due to its asymmetrical and symmetrical stretching. This is the structure of anhydride. Coupling occurs between two carbonyl groups which are linked through oxygen. The interactions become effective probably because of the slight double bond characters in the carbonyl oxygen bond due to resonance, which keeps the system coplanar. It has slightly double bond character and it has slightly single bond character. This interaction becomes effective because all the atoms are present in a single plane because of the partial double bond characters of these bonds. Hydrogen bonding. The exact position and shape of the absorption band depend largely on the degree of hydrogen bonding. Hydrogen bonding usually seems to broaden the band and shift it to lower frequency. Broadening of the peak takes place and shifting to lower frequency. These two phenomena occur when there is hydrogen bonding. A strong sharp absorption peak of OH stretching may appear in a region as high as 3700 centimeter inverse in gaseous or extremely dilute sample containing unbonded or free hydroxyl group. But very broad bands may appear in a region as low as 2500 centimeter inverse in hydrogen bonded compounds. That means when there is isolated OH, it appears near about 3700, and when it is hydrogen bonded case lowers the frequency, so it may appear near about 2500 centimeter inverse. As the degree of intermolecular hydrogen bonding in sample increases, the band corresponding to the free hydroxyl group decrease in intensity. So, when intermolecular hydrogen bonding increases, the decrease in intensity takes place. An additional band appear at lower frequency. Additional one band appear at lower frequency. The degree of intermolecular hydrogen bonding increases with concentration of solution. As concentration increases, the intermolecular hydrogen bonding the degree of intermolecular hydrogen bonding increases with the concentration of solution. As concentration increases, intermolecular hydrogen bonding increases. Thus, intermolecular hydrogen bonding is concentration dependent. Concentration dependent. So hydrogen bonding brings these changes. Increase in bond length. When we consider this intermolecular hydrogen bonding, this OH bond length increases as this hydrogen bonding pulls this hydrogen towards oxygen, and this OH bond length increases. Decrease in force constant. As this bond becomes longer, its force constant decreases. That means the bond becomes weaker, and decrease in wave number. As the bond becomes weaker, the energy required to stretch the bond becomes less. So these are the changes which are occurring due to intermolecular hydrogen bonding: increase in bond length, decrease in force constant, decrease in wave number. Such type of effects of hydrogen bonding may be observed in amines, amides, carboxylic acids. So intramolecular hydrogen bonding causes a greater shift of carbonyl group to lower frequency than the intermolecular bonding. When we consider the example of para-hydroxybenzoic acid, which exist in dimeric form. This is the dimeric form of para-hydroxybenzoic acid. The carbonyl stretching frequency or the wave number value is 1678 centimeter inverse, which is, when we consider in case of orthohydroxybenzoic acid, or it is commonly known as salicylic acid, it is observed at 1665 centimeter inverse. That means the energy required to stretch the CO bond in case of orthohydroxybenzoic acid is less as compared with the energy required to stretch this CO bond in case of para-hydroxybenzoic acid. Electronegativity. As the electronegativity of the bonded atom increases, the shortening of the bond length occur, and large force constant leads to increased vibrational frequency. As bond length becomes short, it becomes stronger, and more energy is required to stretch that bond. So electronegativity, increased electronegativity strengthens the bond. The electronegativity order of the carbon in alkane, alkene and alkyne is alkane, alkene and alkyne. This is the electronegativity order, and same is the case with the stretching vibrational frequency, energy required to stretch that CH bond, this bond. As electronegativity of this group increases, there is more tendency to pull the bonded electrons of CH group and the bond becomes shorter. Eventually, it becomes stronger and there is requirement of high energy to stretch the bond. Electronic effect. In electronic effect, there are three effects, that is inductive effect, mesomeric effect and field effect. Inductive effect. Inductive effect is of two types, that is minus I effect and plus I effect. The introduction of electronegative atom or group shows minus I effect. It results in increase in bond order. So, here is in case of acetone, the stretching frequency is 1715 centimeter inverse. One Cl, one electronegative atom is introduced in the acetone, that is in case of chloroacetone, the stretching frequency increases. Increase in force constant of that bond, or we can say bond order increases. In case of dichloroacetone, one more electronegative atom is increased, the stretching frequency further increases. Similarly, as we go further, you can observe on the introduction of electronegative atom or group showing minus I effect, which eventually increases the force constant of the bond. Mesomeric effect, commonly known as resonance effect, delocalization of the pi bonded electrons, and it appears when there is conjugation. Resonance result in partial pi bond character between the two double bonds. With the decreased electron density and decreased stiffness in bond, conjugated double bond therefore vibrate at lower frequency than the similar isolated double bonds. When it is isolated double bond, it is 100% double bond. This one is 100% single bond and this one is 100% single bond. But in case of 1,3-butadiene, this is double bond, but it is partial double bond, it is partial single bond. The delocalization may occur like this and like this. There is negative charge here, positive charge here, and this single bond becomes double bond. So all the bonds possess partial double bond characters and partial single bond characters. So to stretch the single bond, it requires lower energy, or we can say it requires lower frequency, which corresponds to lower wave number values. So as compared with the isolated double bond, conjugated double bonds vibrate at lower frequencies. Similarly, here also we can say cyclohexene, this is isolated double bond. The value is 1645 centimeter inverse. This is the case of conjugated carbon-carbon double bond, and here the stretching frequency decreases because of delocalization, as explained earlier. In case of benzene, delocalization or mesomeric effect or resonance effect further increases, which further decreases the value of vibrational frequency. The stretching frequency of carbonyl group conjugated with the other electron system are generally lower than those of corresponding non-conjugated compounds. This lowering is due to the partial loss of carbon-oxygen double bond resulting from delocalization of pi electrons over the entire unsaturated area in the molecule. The greater the degree of delocalization of electron, the more lowering of carbonyl stretching frequency is observed. Here we can have the example, as this is isolated carbonyl. It observes at about 1715 centimeter inverse. When this carbonyl is conjugated with the carbon-carbon double bond, there is lowering of stretching frequency 1680, and if conjugation further increases, then the vibrational frequency further decreases. This mesomeric effect causes lengthening or weakening of the bond, leading to lowering of absorption frequency. Lowering of absorption as conjugation increases. As conjugation increases, the absorption frequency decreases. In most of the cases, mesomeric effect works along with the inductive effect, but in few cases, inductive effect may dominate over the mesomeric effect. Finally, field effect. In orthosubstituted compounds, the lone pair of electrons on the two atoms influence each other due to interaction of dipoles through space and change the vibrational frequency of both the groups. This effect is called as field effect. This group and this halogen, they are near with each other through space, and they affect the vibrational frequency of each other. This is known as field effect. The non-bonding electrons present on oxygen and halogen atom cause the electrostatic repulsion. This non-bonding electrons present on halogen and non-bonding electrons present on oxygen cause electrostatic repulsion. This leads to change in the state of hybridization of the carbonyl group, and it makes to go out of the plane of the double bond. Hence, due to diminished conjugation, the absorption occur at higher wave number. An equatorial alpha halogenated cyclic ketone absorb radiation at 1745 centimeter inverse, while its axial isomer absorb at 1725 centimeter inverse. That means equatorial, the value is 1745 centimeter inverse, while this axial form absorbs at 1725 centimeter inverse. Here is the interaction through space is absent or very negligible, we can say. And here, as the equatorial position, there is two groups are in vicinity with each other, so there is repulsion, electrostatic repulsion is there, and which result in absorption at higher frequency. Bond angle, ring strain or strain due to bond angles. The increase in frequency of vibration of absorption bands of carbonyls because of strain due to bond angle can be explained on the basis of increased S characters of the bond of the carbonyl group. The more pronounced S characters shortens the CO double bond and thus increases its force constant. And this is 4-membered ring. Strain increases and absorption occur at 1780 centimeter inverse. Similarly, these are the cases where we can observe very clearly as ring size decreases, strain increases, and the stretching absorption or the absorption frequency also increases as we go to smaller rings. Then let us see conditions for absorption of radiation and selection rule. The necessary condition for a molecule to absorb IR radiation are: first condition is correct wavelength of radiation. A molecule absorbs IR radiation only when the frequency of vibration of a bond in a molecule is equal to the frequency of incident radiation. A molecule absorbs IR radiation only when the frequency of vibration of a bond is equal to the frequency of incident radiation. After absorbing IR radiation, the molecule vibrates at an increased amplitude. And the second condition is dipole moment. When the frequency of electromagnetic radiation is equal to that of alternating electric field produced by change in the dipole moment, vibrational motions are excited in the molecule and the radiation is absorbed. However, radiation is not absorbed if it fails to produce change in dipole moment. So, occurrence of the change in dipole moment is the necessary condition for absorption of radiation. Then selection rule. Selection rule determines whether the vibration would be effective for a particular type of spectrum or not. The requirement that absorption of a vibrational quantum be accompanied by change in dipole moment is known as selection rule. Then what is meant by IR active transitions and IR inactive transitions? So IR active transitions are those transitions which result in change in dipole moment. IR active transitions are those transitions which result in change in dipole moment of the molecule. IR inactive transitions, the vibrational transitions which do not result in change in dipole moment of a molecule, are not absorbed in IR, and these are known as IR inactive transitions. Then two types of transitions are there, that is allowed transitions and forbidden transitions. Only the fundamental transitions, that is transition from a level to next level, that is nu 0 to nu 1, nu 1 to nu 2, nu 2 to nu 3, etc. These are allowed transitions. The overtone transitions, that is transition from nu 0 to nu 2, higher second level, or nu 1 to nu 3, nu 1 to nu 4 also exist and detected as weak overtones in the spectrum. These are known as forbidden transitions. Then fundamental group regions of IR spectrum. Two group regions of IR spectrum are there. First of all, IR spectrum is the graph or the plot of percent transmittance against the frequency in centimeter inverse, or we can say wave number in centimeter inverse. The dip in the spectrum is known as band or peak. And this IR spectrum has two regions, functional group region and fingerprint region. So this is the typical schematic diagram of IR spectrum. The values from near about 4000 centimeter inverse to 1400 centimeter inverse, this region is known as functional group region, and the region of the spectrum from 1400 to 600, it is known as fingerprint region. In functional group region, we can have the peaks or the signals for specific functional groups. For example, hydroxy group, NH, C triple bond C, etc. We can identify the functional group with the help of study of functional group region, and the region which is known as fingerprint region, it is from 1400 or 1350 centimeter inverse to 650 centimeter inverse, and the pattern of absorption in this region are unique to the particular compound, as like our fingerprint. The pattern of signals is unique for particular compound. So this is known as fingerprint region. But in case of functional group region, the pattern is not fixed. The values, we can have the range of their appearance. Pattern is not fixed. In case of fingerprint region, the pattern is fixed as like our fingerprints. So it is known as fingerprint region. These are some of the characteristic absorption of functional groups. This is the range. The absorption frequency may be varying due to the electronic environment or the different factors which affect the absorption frequencies. The frequency range is there. Absorption frequency may increase or decrease because of the factors which we have already seen. These are some of the functional group and their frequency range. Finally, what are the applications of IR spectroscopy? Two main applications of IR spectroscopy, that is determination of structure. To identify the functional groups present in the compound, it is the main application of IR spectroscopy. And identification of the functional group which are present in the compound, it is the key step in determination of the structure. So determination of structure, it is the very important application of IR spectroscopy. Or we can write identification of functional group.